All right, hello everyone. This is our class number 17. We are going to do SVM regression and then see how we can apply it in how we can use Python to do support vector machine regression analysis. We will be working with the same data set that we worked for the classification, SVM classification. So the data set is Washington, D.C. bike share data set. Yeah, because we're all familiar with the data set, let's quickly get into the code and see how we can do SVM in Python, regression in Python. So as always, let me go ahead and run the library. Load the libraries first, the packages. So numpy, pandas, matplotlib, seaborn, and you're ignoring the warnings. Random state 1000. Let's read the data set. This is the head of the data set. We're completely familiar with that. So let me just speed up and then do the data pre-processing very quickly. So this is a clean data set, no NAs. We know that the problem is that lots of categorical variables are stored as integers or as continuous variables. We need to make sure that they're categorical. So our first job is to change those variables into categories, right? So I'm going to go ahead and change season, year, month, hour, holiday, weekday, not a business day, and weather situation as categories. And then if you look at the info, you'll see that all of them are changed to categories. Then for regression analysis, we're going to get rid of this dates variable as well, because we're not going to use it. And in regression analysis, we can look at the pair plot, but we don't use the colors because our target variable is continuous. So the reason that I personally want to look at the pair plot, if the data set is relatively large like this, 17,000 observations, it's going to take a little time. So if you want to plot all the variables, so what I recommend you to do is that at least make sure that the first variable that you have to take into look into is the target variable. So count is our target variable here. And I want you to look at the distribution because this is really, really important. When you're doing regression analysis, the distribution of the target variable is really important. So that's something that for sure you need to look into. And then the distribution of the X variable is not necessarily important, but if you're doing scaling, if you're scaling the features, then it becomes important. So it seems to me that, well, at least if the continuous features are, I can say they are relatively normally distributed, or actually close to normal distribution, right? So this is something that you should keep in mind that if you want to do standardization, using the z-score normalization, this is not a bad idea to do that because look at the distribution of the features. They are relatively normally distributed. So I'm not concerned. However, when I look at the target variable is super right skewed. First of all, it cannot go negative. Well, the negative does not matter. What matters is that there's no left tail here. So the right tail is very long and basically it's heavily right skewed. So in this exercise, I didn't do log transformation, but you can go ahead and do log transformation in order to just shrink, maybe minimize that large right tail. It's going to help. So, but it's not going to make your target variable closer to normal. It's going to make it closer to normal, but it's not necessarily normal. So I know by looking at the distribution for the counts, I know that doing log transformation is not necessarily a bad thing, right? So just keep in mind. So the takeaway from this plot is my features are relatively normally distributed. My target variable, if I do log transformation, it's not going to be bad. However, I remember. So in this case, I didn't do log transformation because there are many variables that are exactly 0. The count is 0, so you cannot do log transformation. But again, in general, if your variable was anything positive, greater than 0, and it was distributed like this, it's a good idea to do log transformation. Okay. All right. Then let's scale the features. As I said, because most of my continuous feature variables are normally distributed or close to normal distribution, I'm going to go ahead and use the standardization, right? And by standardization, I mean z-score normalization. Take the average out divided by standard deviation. But before that, I have to make sure that all the categorical variables are transferred to dummy variables. Because remember, guys, this is a very big important step. If you do not change the categorical variables into dummy variables, you're going to completely confuse the algorithm. The algorithm is going to overfit the model, and you're going to completely lose track of the variables. For example, look at the weekday. We have weekdays. We definitely know that the order, we have 1, 2, 3, 4, 5, but the magnitude doesn't make any sense, right? So 2 is not twice as important as 1. 6 is not twice as important as 3, and etc. Right? So for that reason, we have to make sure that these are dummy variables, right? And when we do this get dummy, by the way, this is called, if you read somewhere that one-hot encoding, this is what we call one-hot encoding. If you make variables into dummy variables, it's called one-hot encoding. Okay. And so let's make them dummy variables. We can look at the head of the data set very quickly. So this is before a standardization. So I make sure that the weekdays, we dropped the first one, I believe. Yeah, the first one is dropped. So we, for example, we have weekday 1, 2, 3, and etc. I think it started from 0, but we dropped the first one. And now you're doing standardization. We will use z-score normalization. So let's say my scale is a standard scalar. I'm going to fit transform, and I fit transform to the entire data set. I will talk about this in the second part of the class today, that usually it's a better idea if you fit transform to the train set, and then you transform the observation in the test set using that fit, because otherwise there's a chance that the data is leaking from test set to train set. However, in this case, I went ahead and transformed the entire data set. There is a reason, because I checked both ways. There's not much difference, and I wanted to save that argument in the second part of the class. So, and I'll tell you how to do that. If you want to make sure that there's no information leakage from test set to train set. Okay. So so here, now this is the data that it's ready to be passed to our algorithm, SVM regression. And as you can see, all the variables now are standardized, and definitely I have, we made sure that the categorical variables are dummy and then standardized. So we have 53 columns, and so this is relatively high dimension, right? So it's not super high, but it's not 5, 10, it's 50. So we know that KNN is going to have a hard time handling this model. All right. Now, the rest of the, I think the rest of the code is pretty straightforward. We're going to go ahead and define our target variable and features. So the target variable is the count, and the features is anything else but count. So now we have our train set, test set. We split using the 30-70 ratio. So 30% test set, 70% train set. And now this is the part that we are doing. Again, usually the machine learning algorithm is in four lines. So that's all we do. All right, so let me pull up the contextual help quickly. Now load the SVR, and as for a starter, we are going to fit the train set using the let's call it the blank model by using the default inputs, right? Let's look at the inputs of the SVR. So by default, the kernel is RBF, degree is 3 if you're using the sigmoid kernel, the polynomial degree. Gamma scale, we talked about this last class. And then what else do I care? No, C is 1. Epsilon, this is new. In classification, we didn't see this epsilon, right? Do you remember? In regression, we do see epsilon. Do you remember what is the epsilon? That was actually, it's good to remind you that what was the epsilon. So if I go to the theory part, so this is where we talked about the epsilon. Here, these are the epsilon, right? So the epsilons, I told you that this is not a hyperparameter. We don't play around with that. We usually set it as, so by default in Python, the number is 0.1. Yeah, it's 0.1. And the algorithm is trying to make sure that the majority of the observations are within this margin, right? So that's how it's done, right? So the epsilon is a new thing that we have in regression, but not in classification, okay? Then, yeah, that's pretty much it. All right. Now, again, we're going to fit the model using a train set. And the SVM, because we have 17,000 observations, and by default it's using RBF, it's going to take a little time. It's faster than the linear kernel, but still, as you see, I think it took 8 seconds, 9 seconds. We are going to do grid search cross-validation, and we'll see that it's going to take time. All right, then we make predictions. The output of the SVM predictions, these are some continuous numbers, right? Because the output, if I compare y versus y hat, so this is the actual value for y, this is the predictions. So we're quite completely familiar with the concept of regression, right? We can plot the y versus y hat and see if it lines up against the 45-degree line. We can calculate the R-square in the test set. We can calculate the RMSE and et cetera, right? Let's go ahead and do that. So if I plot the y versus y hat, actuals versus predictions, yeah, it's doing a decent job. And by the way, this is in the test set, right? So in the test set, it seems that it's doing a really good job, even the default values of the SVR function, right? I can look at the R-square in the test set, and I'm not concerned that this is R squared. Guys, so maybe it's a good idea to ask you a question. Why do I not care that this is R squared and it's not adjusted R squared? The dimension is 53. Why I'm confident that I can simply use R squared instead of adjusted R squared? Because if it was econometrics, remember, the dimension is high, and we know that we have to do adjusted R squared. But here, why am I not concerned? We talked about this in the class. What do you think?
Sample size is too large.
No, this is not the sample size. No.
So the features are large.
No, features, again, that's a counter argument, right? Because if the dimension is high, I really want to work with adjusted R square, not the R square. But here I'm not concerned that I'm relying on the R square. Because this is R square in the test set, right? So do you remember we had this discussion that, okay, we have R square, we have adjusted R square, but if I'm reporting the R square in the test set, it's automatically taking care of that overfitting for me, right? So if the R square in the test set is, let's say, is high, I'm confident that I'm not synthetically increasing that number. Because if it was in the train set, if I increase the number of dimensions, R square is going to automatically increase, right? But if I'm doing it in the test set, automatically it's going to avoid that issue. Okay, so that's something good to keep in mind. You can go ahead and calculate the adjusted R square as well, but there is no built-in function in R, so you have to do it manually. So you have to use a formula for adjusted R square and then manually construct it. But you don't need to be worried about it. As long as you're reporting the R square in the test set, you should be in good shape. Then I can report the RMSE, and it's 0.26. If you compare these numbers with the KNN, I think in KNN, the R square in the test set was around 70%. Now it's 93%, so it's a huge improvement. And the same story for the RMSE. I think it was around 0.55. Now it's only 0.26. So huge improvement over KNN. So, and this is something expected, right? Because the dimension of the data was large and lots of categorical variables. And I knew that SVM should do a better job. All right. Now let's do an exercise together. Let's try C is equal to literally 0. As I said the last time, we cannot put C is equal to 0 because it's going to complain. So we can put a very small number. Let's do, I don't know, 1 over 10,000, right? Okay, so before running the model, what do you expect to see here? If C is super small, what will happen? Go back to the theoretical part of the SVM regression. If the cost of adding those slack is literally 0, then the algorithm is going to somehow completely ignore those slacks, increase that number. So eventually, we're going to get a simple line. Does everybody agree? If that C is large, then the decision boundary here, our regression is going to bend over a little bit. But if C is very small, the algorithm is not penalizing the slacks, so it's going to come up with a very simple line, and that line is going to be the average, right? So let's run. Let's see if we get that average line here. So this is running, is plotting y versus y hat, where C is very small. And see, what the model is going to predict is awful, right? Because it's going to always predict the average. And by the way, guys, remember, this is a standardized counts, and we know that there were lots of zeros. So zeros are going to become negative when I do z-score transformation, and the average is a negative number. And we know that this is not true. This is not a good model, right? Because C was super small. So I can go back and change to C is equal to 1. All right. When it comes to tuning hyperparameters, exactly the same story that we had for SVM classification, right? We have to use GridSearch cross-validation method. And the parameters, the hyperparameters that we are interested in are C and gamma and the kernel itself, right? So here we're going to go with randomly we choose these numbers, but these are not completely random, right? So based on application, lots of optimizations out there. Usually we know that if you look for C is equal to 1, 10, 100, this is a good start. Gamma 1.1, 1%, and 1 over 1,000, this is also a good start. And there's literature that shows that random search like this many times outperform more optimized GridSearch cross-validations like using gradient descent, right? So this is a question that Grayson asked. It's a very deep and good question. I'll talk about it. I'll talk about it more. So there's literature that literally shows that random search, maybe educated guess, is better than relying on gradient descent because of non-convexity of the objective function, and the algorithm is going to most probably stuck in one of the local minimums. Okay, or maximum, whatever the objective function is at. And most importantly, this is important. Let me actually discuss it here. So the question is that when we are tuning the hyperparameters in SVM regression, can we be more efficient, right? Instead of trying random numbers like this, can we be more efficient? And by more efficient means that can I trust, for example, algorithm like gradient descent to go ahead and find the optimal value for that continuous hyperparameter for me, right? Because remember, guys, if the hyperparameter was discrete, I could use cross-validation and do the ALBA method and see where the optimal value of K, for example, in K and N is, or the optimal degree of the polynomial is, right? If the hyperparameter was continuous, like lambda in penalized regression, and the objective function was very well behaved, if you look at the objective cost function in the penalized regression is very well behaved, so we can do gradient descent to find that lambda, right? However, here there are multiple issues that we can try gradient descent to automatically find these C and gamma and kernel, but there are some issues that we should be aware. First of all, we have multiple continuous hyperparameters, right? So it's going to increase the computation time, right? That's not necessarily an issue. The bigger issue is that we have a categorical variables. This kernel can be 4 classes, right? RBF, let's say, sigmoid, polynomial, and linear, right? And the combination of the two can make the objective function have a non-convex behavior, right? And this non-convex behavior is going to be a pain for gradient descent algorithm, right? And the reason is that we say the objective function is not going to be well behaved, and most probably the algorithm is going to get stuck in one of the local minimum maximums. And as I said earlier, there's literature that shows that these random search are usually outperforming the more efficient, let's say, gradient descent kind of optimizations, right? I hope that you're realizing at least barely what I just said, because this is an important topic. Okay. Just be aware that if you're doing SVM, we have to do it this way. This is going to be faster, more to the point, and hopefully finding the global minimum. But it's not guaranteed, right? Because here I'm only trying 3 numbers and 3 numbers here, and maybe only 1 kernel. But who knows? Maybe I could get a better number. All right, then. This is going to take a while. I don't know if it is worth if I run it because yeah, it's going to take 4 or 5 minutes. Let me read through the rest of it because we don't need to run it in the class. You can try it at home, depending on the speed of your computer. So we are trying 9 different combinations, right? 3 of C's and 3 of gammas, and only 1 kernel. So 3 by 3 by 1 is 9. If I do 5-fold, so it's 9 multiplied 5, it's 45 basically fits. So if you run this, I'm not going to run it here. You will see something like this. So basically, I have 45 fits, and some of them are going to take longer than the other ones. And it's very intuitive, right? So for example, if kernel is linear, you'll see that this goes from seconds to minutes. If I'm decreasing gamma, it's going to be a lot faster because you're reaching out to further points. And you can come up with the I think justification why these maybe running times are different for different values of C. Okay. All right. Then after we do grid search cross-validation, we can look at the best parameter. So the best parameters turn out to be 10 for C, and gamma is 1%, and kernel was RBF, right? Then we can come up with our optimized y-hat. So I call it optimized y-hat because I just want to compare them side by side. So this is going to be the prediction out of the grid. The reason that I can do grid.predict is we have refit is equal to true. If the refit is not equal to true, you have to manually do this process again. It's not that long. You just simply write SVR and then pass the optimal values, right? If you don't want to do that, you can simply do grid.predict. All right. Then, so this is the y. This is actual y. This is what was predicted. And this is the optimized version. As you can see, the optimized version is closer. We should not be surprised here because actually the algorithm went through all the combinations and gave us the best one, right? Now I can look at the y versus y hat in the test set. So it's going to outperform the basic model just slightly, right? So the R square used to be 93, now it's 94. And I believe RMSE used to be 0.25. Yeah, 0.26, now it's 0.24. So it slightly improved our algorithm. I think this is something that I discussed last class as well. You know, if you run the models, whatever algorithm that you're working with, KNN, SVM, logistic regression, whatever, if you run them with the default inputs, okay, and then try to optimize the hyperparameters, usually you cannot improve it dramatically, right? Usually it's a couple of percent if it is R square, and depending on the scale of your target variable, it can be some points in the RMSE, right? Because the default inputs in the, at least in Python package, the default inputs are chosen wisely, right? It came out of thousands of simulation, and so that's why, for example, we know that RBF is going to outperform in many cases, so the default kernel is RBF, right? Or C1 is going to outperform in many cases, so we are going to use C is equal to 1. All right, so that was our support vector machine regression, how we can do it in Python. Is there any specific question from the code? The reason that I was a little fast because I know you guys are familiar with all the codes. So the only new part was this one, and we talked about what are the different inputs in the SVR. So if there's any other questions, I can move on to the second part for the class today. Guys at home, any questions? Okay. So let me pause the recording here.